A classic mathematical problem, but the solution was unexpected. Newton used pure mathematics to calculate the length of a day and a night. But the most ingenious solution came not from mathematics, but from optics. Imagine you want to move a small ball from point A to point B in the shortest time. It sounds simple enough. A straight line is the shortest distance between 2 points. But if you could curve the slope, the ball would gain more speed initially, making it travel faster, while the distance would be slightly longer. The overall time would likely be shorter. So the question arises, is there a line that perfectly balances acceleration and distance? This problem was first posed by Galileo Galilei, who hypothesized that the curve would be a circular arc, but he was later proven wrong. It was Johann Bernoulli who made the problem famous. In 1696, Bernoulli addressed the problem in an open letter to his brother. In the letter, Johann emphasized, "I already know the answer, but I'm keeping it secret for now." His main purpose in writing the letter was to show off his prowess, as public challenges were a popular way to boost one's reputation in European academic circles at the time. However, after the problem was posed, no one submitted an answer for several months. John's friend Leibniz urged him to extend the deadline to give foreigners a chance. Bernoulli's real challenge was actually to Newton. Newton was 53 years old at the time and rarely did research. But the problem was so intriguing that he spent a day and a night trying to figure out a solution, and by the next morning, he had it. Bernoulli spent 2 weeks on the problem. Newton anonymously sent his solution to a scholarly journal. He wrote in his submission, "I don't like being rushed or ridiculed by foreigners." It said that when Bernoulli saw the newspaper, he immediately recognized it as Newton's solution. He said he could recognize the lion from its paw prints. Newton used his own tool, calculus, to solve the problem. He first assumed the curve was a function, then applied the principle of conservation of energy to deduce the ball's speed at a certain height. Finally, he calculated the time taken for the entire journey. He worked through the night to solve the equation. Bernoulli's inspiration came from a very old question. How does light propagate? Light always travels along the shortest path within a medium. However, when light passes from one medium to another, it refracts, changing its path. For centuries, Snell's law described this, but no one understood why light follows this path. It wasn't until 1657 that Pierre Fermat offered his answer. He proposed that the path chosen by light isn't necessarily the shortest distance, but rather the path that takes the least time. He spent 5 years researching this, ultimately proving that the essence of Snell's law is the principle of minimum time, and that the refractive index holds the key to the shortest path. Inspired by this, Bernoulli transformed the problem of the brachistocentrism into an optical problem. He imagined the acceleration of a falling ball as the path of light refracting through different media. Assuming that space can be infinitely divided, with each layer corresponding to a different speed, as the ball passes from one layer to another, it will, like light, choose the path that takes the least time. If you plot the incident and refracted rays of light layer by layer, you'll eventually get a curve like this. This is the optimal path chosen by nature. After calculating, Bernoulli recognized the simplified equation, a cycloid. Simply put, if you hold a pencil to the edge of a circle and move it along a straight line, the path traced by the pencil after the circle completes a full circle is a cycloid. This cycloid has 2 remarkable properties. It's the fastest path of descent, and no matter where you start on the curve, it takes the same amount of time to reach the bottom. Therefore, it's not just a brachistocentre curve, but an isochrone curve. Before the deadline in 1697, Bernoulli submitted his own solution. He proudly wrote in a letter, "My method solves 2 problems at once, one in optics, the other in mechanics." Later, in a letter to his brother, he acknowledged the efficiency of Newton's solution, while both theirs were somewhat clumsy. But with this last line, it's unclear whether he was being sarcastic or referring to his brother. While Newton's method was straightforward and quicker, Bernoulli's approach transcended scientific boundaries, using physical intuition to solve mathematical problems. This line of thought has sparked a series of scientific discoveries, and perhaps this is what makes science so fascinating. When different disciplines converge on an unknown problem, we discover a whole new world.